recording. Can the domain and range of the function have the same values? And I mean, can the output numeric value equal the output or the input numeric value? Can that happen? And then also, can the domain and range of a function not intersect? So in other words, the values you can put in, and they're not going to be the numeric values that you put out. So starting with the first one, yes or no? In the chat, everyone, yes or no? Can the domain and range of a function be the same? Yes or no? Now I'm seeing a lot of yeses. Is anyone willing to unmute themselves and give an example in which your domain and range will have the same values? Is anyone willing to unmute themselves and give me an example of when the domain and range will be the same? So the example was when we have the function f of x is equal to x, which is the same thing as saying y is equal to x. So yeah, so in that one, your domain is everything from negative infinity to infinity, and so is the range, negative infinity to infinity. What about the domain and range of a function that don't intersect? What do you all think on that one? Domain and range in which they don't intersect. And the answer actually is yes. You can have a domain that has all real, or you can have a domain that has only positive values and your range is only negative values. So you could have a graph that looks like this, which is totally a function. All of your inputs are positive numbers, but all of your outputs, and you don't get to include 0 on your outputs, could look like that. So you could have a line or any other graph in which all of the outputs are negative, but only your inputs are positive. So you can absolutely have a function in which the domain and range don't have any values that they share, numeric values that they share. So it absolutely can happen. With that said, that's going to introduce us into piecewise functions, which is what we're going to be doing today. So what a piecewise function is, it's a function in which I have different pieces and I have different domains for each piece. So unlike the example up above where I have domain and range and I have a nice little easy identity function, it's called the identity function, and I put in whatever I put in for x, I can put it in anywhere. There's no restrictions on the domain, and I'm going to get a nice output that's going to be the same thing as what I put in. But with a piecewise function, you have different values based on different output values based on how it's defined for the domain. So when we're talking about an absolute value function, what an absolute value function truly is a piecewise function. It has one piece of the graph, which is on the left side of 0, and it is going to be negative x. And then you have a second piece of the graph, which is going to be on the right side of 0, and that's going to be positive. So if you were to graph the absolute value function on the left side is in green, and then on the right side is in red. So what I have with an absolute value function is I have two lines. I have two different pieces that are defined based on the left side and the right side of where the two lines intersect. So a piecewise function is something that we see when we're looking at an absolute value function. So let's talk a little bit to get the abstract more concrete, because this is a pretty abstract idea, and make it more concrete. So say that you have a cell phone and your data plan is that for your base rate of your cell phone, the base rate is $50 a month. And then if you use data and so the base rate is not including data. So the base rate is you're just using calls. So there's no data. So if you use data, so for the first, I don't know, a gig, is a gig, I should have asked my husband who's a geek and I don't know this, is a gig something large? Yes or no, is gig something large?
It's the standard unit.
Okay, so then we'll go with, so for the first 2 gig, so up into the first 2 gigs, you add $10. And then once you pass the 2 gig mark, so from 2 gigs to say 5 gigs, the plan adds $20. And then if you go over 5 gigs, they're going to charge you, I don't know, $75. So for this one, if you are just using your cell phone and you're using it for calls, you're not texting, you're not using any data, you're going to pay a base rate of $50. Now, the moment you start using your data, which includes your texting and all that, then you're going to have to add $10 onto your plan. So your plan is no longer $50, it's $60. Now, you start using a lot of your data up, you start going through the data, and you get past that 2 gig mark, but you're 5 gigs or less, you're going to pay $20. And then if you go over the 5 gigs, they're going to charge you another $75. So you have 4 different pieces to this plan and how much you have to pay. So just as a public service announcement, if you need a hotspot, they still have some hotspots there. Contact the library. There are some links in Canvas to get you to the library. You can ask them about getting the hotspots. They are free to you. If you don't return it, they do charge you for it, but they are free, and that way you don't have to go through your own data. Just saying. Okay, so if I were to build a function on this, f of x, x being, let me see, x equals the data. So I got to tell you what because it's an application, I need to tell you what x represents. So x represents the data. So your first one is $50, and that's when you have no data, when x is equal to 0. So when you have no data, you're not using any data, you pay $50 a month. So then if you use some data, you're going to have $50 plus the $20, or excuse me, the $10, and that's when x is greater than 0 and less than or equal to 2. So when x is greater than 0 but less than or equal to 2, you're going to be paying basically $60. And then if you go over 2 gigs but less than or equal to 5, so that's going to be 50 plus the 20, and that's when x is going to be between 2 and 5. And then the moment you go over 5 gigs, you're going to do 50 plus that $75. And that's when x is greater than 5. I had 4 different pieces, so this is my first piece where I'm using no data. The second piece is when I am using some data. The third piece is when I start using more data, and then the fourth piece is when I'm using the most amount of data. So if I wanted to know how much my bill is going to be at various stages, so when I have 1 gig, when I have 2 gigs, when I have 6 gigs of data that I am using, I need to determine how much my bill is going to be. So in the chat, tell me where I would expect to see which piece would I use, the first, second, third, or fourth piece for 1. If I have 1 gig of data, which one would I use? 1, 2, 3, or 4 in the chat? So it looks like I've got number 2 is what most people are saying. I've got a couple of question marks on number 2. So I ask myself, I have the number 1. And then I look to see where on my pieces did this lie. Well, number 1 is not here. It's not 0, so I don't have to worry about putting it in that one. And then 1 is in this region between 0 and 2, and so I'm only going to put the number 1 in that region. And so when I'm evaluating 1, if I use 1 gig of data, my cell phone bill that month is going to be $60. Now, for 2 gigs, which data plan or which piece am I going to use? 1, 2, 3, or 4, or more than 1? So on this one, which one do I use? Piece 1, 2, 3, 4, or more than 1? Go ahead and put this on pause. Okay, looks like everyone's in agreement on number 2, the second piece. And again, that's because we have inclusive on piece number 2. Piece number 3 is non-inclusive, so I'm not going to put it in piece number 3. I only put it in piece number 2. So as long as I have 2 gigs or less, I'm going to pay $60. Now for the last one, I have 6 gigs. Which piece am I going to use? 1, 2, 3, or 4? And that was pretty quick. You all responded fairly quickly on that one. It is number 4. And that's because the only place I put it in is where it's defined, and it's defined where x is greater than 5. So this is going to give me an answer of the 50 plus 75, which is going to cost me $125 that month if I went over 5 gigs. And when I go to graph this, I have 4 pieces I have to graph. So I'm going to come down here and I'm going to graph these 4 pieces. So the first piece is when I have 0 pieces of data, I'm at 50. And that's my first piece. My first piece is just $50. So the X represents the data used, and the Y represents on this one, the Y represents the cost. Because this is an application, I have actual values that I can put in, which makes sense. It's not as abstract. So the moment I get past 0, I am going to have, so I have 2, I have 5, and then I have everything beyond that. So this 50 represents the first piece. So if I don't use any data, I have $50 I have to pay. The moment I get past 1 gig of data, then I have to pay $60. So I'm going to put an open dot right above that and all the way to 2, and then 2 is going to have a closed dot. The reason 2 is going to have a closed dot is because right here, this is for 0 less than, that's why that is an open dot. And then we have x less than or equal to 2, and that's why that is a closed dot. So that's what that piece is going to do. And so that piece represents the second piece of my domain. My next one is that as soon as I get past 2 to 5, so an open dot on 2, a closed dot on 5, so this is 60, this represents 60, this represents 70. So this is my third piece. And again, this is an open dot because this is 2 is less than x. So that's why it is an open dot, because it's not inclusive on the left side of this piece. And then this is a closed dot because we have x less than or equal to 5. So we will close that side. And then my last one is when I'm above 5. So above 5 is represented with an open dot and then goes in that direction. And that would be way up at 125. Clearly not drawn to scale. So that's what a piecewise function would do, is you graph it by the domain based on how it's defined. Now I'm going to stop and I'm going to give you a couple of moments to think about what kind of questions you have for me. And you can either put them in the chat or you can just unmute yourself. But I'm going to give you a minute or so to think about what I just did, how it's graphed, and why I have open dots and closed dots and how did I decide that. So I'm just going to put this on pause for a minute. Before you ask me the questions, I want you to think about what kind of questions you would like to ask me, so that when you go to do the homework or you go to do the quiz, you're like, I know how to do this. So put this on pause. All right, so the first question I have is, so there are 4 pieces. Yes, I have 4 pieces I have to graph because I have 4 different sets of domains. So I look up here and I see I have my first piece of my domain. So I have to graph that piece based on that domain. And then I have the second piece of my domain. And then I have the third piece of my domain, and then I have the fourth piece of my domain. Because I have 4 different pieces, I should have 4 different pieces on my graph. So here's the fourth one, here's the third one, here's the second one, and then this dot is just the first one. So that's going to tell me how many pieces I need based on how my domain is cut up. My domain is cut up in 4 pieces, so I need to have 4 pieces on my graph. What other kind of questions do you have for me? You can unmute yourself and ask the questions too, because when I'm hooked up to my iPad like I am right now, I can't see when you raise your hand. The only time I can see when you raise your hand is when I'm not on my iPad. So it's a glitch. It's all good though. So if you want to unmute yourself and ask the questions, by all means, please do.
About was the set builder notation, right?
Yeah. So it's basically because of the fact that we're looking at certain pieces, we are taking a piece actually of the set builder notation, the piece that is the part that comes after that straight line such that. And so yeah, that is how we do it, is we break it apart with the set builder notation with that one piece of the set builder notation. And what I mean by that is, if I look at my set builder notation, I have x such that, so the piece on the piecewise function that we use is what's in this region right here. So yeah, that's kind of like the set builder notation is what we're using here. What other kind of questions do you have for me? Go ahead and unmute yourself and ask the questions. Nothing? All right, so if there are no further questions, then we're going to go ahead and give you some examples to work on. I want to erase that so we can get you over here. Okay, so for this example, go ahead and find f of -3, f of 1, and f of 5. So I'm going to go ahead and put this on pause and give you an opportunity for you all to find those 3 pieces and deciding which ones they're going to go into.
And we're given 3 parts of our notation. So our first number here, f of -3, we're going to search for whichever part of the set builder notation -3 applies to. So the x squared at the beginning here, it's for any number that is less than or equal to 0. So we plug -3 into x squared, we get 9. Our next number, f of 1, we look for where 1 would apply in our set builder notation, and that goes in the second set, because it's for any number that is greater than 0 or less than or equal to 2. So f of 1 is equal to 4. And then f of 5 lies in the third set, because that's any number that's greater than 2. So we do 5 minus 1, and we get 4.
Thank you. Does anyone have any questions on that? Yeah, you did a really good job, Thomas. Thank you. Anyone else have any questions on that? Okay. Did you see how we did partnership? I was, drawing on this. I'm so self-amused this morning. Okay, so what we're going to do now is we're going to graph these things, and we're going to graph them based on the piece. So one of the things that is beneficial when you're graphing these is to consider breaking up the graph with the dashed lines to remind yourself where it breaks from one graph to another. Now, I'm going to let you all do that one. How many do I have? Yes, okay. So I'm going to do this one up here, right below it, or actually I'll do it off to the side. And so when I graph this, what I do is I break it up into how it's defined. So my first piece is anything that is less than 0. So this is my first piece. So anything that is less than 0 will be on the left side of 0 and inclusive. The second piece, and I'll do this in blue, is defined here between 0 and 2. So anything that's in between 0 and 2 is going to be graphed in that piece. And then anything that is greater than 2 will be graphed in that piece. So my first one is x squared. Now, if you're not familiar with x squared, that's cool, because we will get to graphing, or we'll learn how to graph quadratics. But x squared is going to have a shape that looks like this. Now, the other way of doing piecewise is you can actually do a chart, and that, especially if it's a shape that you're not familiar with, the x squared, you can do a chart. So that's my x squared, and because this is inclusive, I'm going to have a closed dot right there. Then my next piece, which is in the region where the blue is, it's going to be 4. So here's 4, and it's an open dot because this is non-inclusive. And then it's going to go all the way to 2, and it's going to be closed. And so that's what that piece looks like. And then my last piece is x minus 1. So for my last piece of being x minus 1, I need to figure out where I'm going to need to start on my dashed line. So I'm going to put in 2, even though I'm not going to have a closed dot. I do need to know where it is on my dashed line. So I'm going to put in 2. So when I put in 2, 1 comes out. And so what I have is at 1, I'm going to have an open dot, and then it's going to go up like that. And so that's the different pieces of my graph. Now I'm just going to take off how I put my dashed line, or my values underneath, so you can clearly see the graph in each piece. So when you're doing a piecewise function, consider putting dashed lines in there so you know where it breaks between piece to piece. Now I didn't do a dashed line along the y-axis because it is the y-axis. I could have just put it right beside it. But anyways, that's how you graph it, is by looking at the domains. And you break it up based on the domains. Notice the green line does not go any further on the left-hand side than the dashed line. Just like my quadratic doesn't go any further after I go past the y-axis. And my blue line is contained between 0 and 2. So when you're doing these, they still have to be a function. And what I mean by that is, right here, if I would have had these both being closed, then it would no longer have been a function. And the same thing is true here. If I would have had both of those as being closed dots, it wouldn't have been a function, because it would have hit the graph twice. It would have hit it both at the left side and the right side of 2, so that's a problem. So whenever you're graphing a piecewise function, and you have 2 of them that come together, one will be a closed dot and one will be an open dot. Or they may both be open, and the way you're going to determine that is looking at the inequalities as it's first initially set up. So with that said, I want you to go ahead on your pieces of paper and graph these, as well as evaluate 1, -5, and 10, please. I'm going to put this on pause. All right, is anyone willing to unmute themselves to tell me what they got when they did the evaluation part of it?
Well, for f is equal to 1, we find that it fits into the second piece, where -3 plus x squared is the case. So we go to -3, and then we add x squared, so 1 times 1 squared is 1, so -3 plus 1 is equal to -2.
Okay.
Then for -5, we see that 5 is greater than 2, so it fits the third piece, where it would be x divided by half plus 1. -5, I'm sorry, that would be the first piece because it's less than or equal to 0. So it would just be 3. Then finally at 10, that one is greater than 2, so we divide 10 by half, and then we subtract 1, which would be 5 minus 1, which gives us 4.
Is there any questions on the evaluation part of it? Okay, cool. So let's go ahead and graph this. So when we graph this, we're going to break it apart between 0. So here's when x is equal to 0. And then also at 2. So I'm going to do when x is equal to 2. So anything on the left side of 0, I'm going to get -3. So I'm going to go down to -3. And it's a closed dot because of the fact that we have an equality there. So I'm going to have a closed dot on this piece. On the next piece, which is the in-between here, it's going to start at -3 and it's going to go all the way up to, well, I have to put in 2 in there. And when I put in 2 in there, I'm going to get 1 out. So it's going to come all the way up to 1 right here. This is going to be a closed dot. It's going to be kind of curved like this. And this has an open dot on top of a closed dot. Because I have 2 that are coming together, the one that it's going to dominate because they're coming together at a single point is going to be the closed dot. So even though my in-between piece is not inclusive, the dot that is dominating that will be the one on the other side, so it will be a closed dot there, make it really large closed dot, and it will dominate the open dot. So even though they come together there and one is closed and one is open, the closed dot will dominate that point, and so it will be inclusive because it's just the way it is. Domination, absolutely. World domination, almost like dot domination. Okay. And then my last piece, which is what I'm going to do in green, is it's going to be open at 2. And so I've got to figure out where it's going to cross that dashed line, however. So I'm going to put 2 in there just simply because I need to know where it's crossing the dashed line. So I know where to put my open dot on that dashed line. So I'm going to put 2 in there and I end up with 1/1, which is 0. So I'm going to have an open dot here. Do that in green. Have an open dot at 0. And then from there, it's going to have a 2-1 slope. And so it's going to look something like that. And so there's my piecewise function. I have 3 different pieces because I have 1, 2, 3 different domain breaks. So because I have 3 different domain breaks, that tells me how many pieces I should have with a piecewise function. Does anyone have any questions, or actually, what kind of questions do you have for me on piecewise functions? I'm going to give you a moment to think about it. So before you unmute and or type in there, let me know what kind of questions you have for me. So give me a moment to think about it. And then when I see you all on Monday, we'll pick up 1.3. So I will go in to my open math this morning and into WebWork and change the due dates. And I'm going to start tagging which each quiz is based on which sections, so that if I have to push back, you know which ones that you have to do by the time they're due. So in my open math, I'm going to change them, and so there should only be like 1 or 2 quizzes, or maybe 3, but I think it's like 1 or 2 quizzes. All the rest will be pushed back into next week. The same thing for the homework. And if you've done the quizzes this week, cool. Means you're just working ahead. If you haven't, that's okay too. Okay, who I have not heard from, so not Matthew today and not Thomas, who would like to unmute and then help me out as to how to evaluate this? I am going to simplify this thing first before you do anything else. So simplifying is x squared minus 4 becomes x minus 2, x plus 2 over x plus 2. And so that's what that factors into for the first piece. Those two do cancel, and you end up with x minus 2. So who would like to unmute, not including Thomas, because you gave me some answers already, and not including Matthew. Who would like to unmute and tell me how to evaluate -2, 1, and -1, please? I'll just call on somebody if you don't unmute. All right, so I'm just going to call on somebody. Let's see. Cade, go ahead and unmute, and can you hear me and unmute? Give me the answers for the evaluation. I'll just go down from the top. Ashton, could you unmute and give me the answers for the evaluation?
I didn't finish it, and I got f of 1 wrong.
Okay, that's okay.
So-
That's okay. I am fine with you getting the wrong answers. You don't have to have the right answers, because every time you get the wrong answers, it gives us an opportunity to learn from it. So this is a class where it's totally fine to get the wrong answer. You don't have to have the right answer. By the time you take the test and the quiz, you do, but this is learning how to do it in class. That's totally fine. So when you did f of 2, f of -2, which piece did you put it in?
I did f of 1, and I got -3 over 3.
Okay.
I
And then,
did 1 squared minus 4 over 1 plus 2.
okay. So when you did that, you got -1 squared minus 4 over -1 plus 2. In the numerator, you've got 1 minus 4, yes?
Yes.
And then in the denominator, you ended up with just +1.
Yes.
And so what is your final answer then?
-3.
Okay. So that is it. Your answer should be -3.
Oh, high fives. High fives.
Absolutely. So -2, which piece do you use, Ashton? The first one or the second piece?
I didn't do that one.
Okay, well, that's okay. Let's do it together. So I'm looking for -2. Do I put it in this first one, or do I put it in the second one? Where's
The second one.
Yep, the -2 is defined in the second one. So that answer is 3. So then -1, is that defined in the first piece or the second piece?
What was that? Sorry.
That's okay. So for -1, when you're asked to evaluate -1, does that go in the first piece or the second piece?
Oh, the first one.
It goes in the first one. So I'm going to use this simplified version. If you put in -1 in there, what comes out?
A -3.
Yep, -3. So I think I did a mistake on that first one because it's +1. Sorry, it should have been a +1 in the denominator and a +1 in the numerator. And you probably said +1, and then I was just off on my own little tangent world this morning. That happens to all of us, by the way. So going back to this one, you get 3 over 3, 3 over -3, so you get -1. It's probably what you got, and I just kind of didn't listen well this morning because I'm tired, just like you all are tired. Okay, so that's the evaluations. If you were to graph this, oh, that's not what I wanted to do. If you were to graph this, you end up with the line y equals -2, y equals x minus 2. And so this is what the graph is going to look like. It is, when this simplified, it simplified into x minus 2. So at -2 is my intercept, and it has a graph that looks like this. Here's my graph, here's my line. But at -2, I have a hole, so I'm going to have to put a hole right there at -2 in my line because that is not defined there. And so what I put in for it is I put in 3. So right there is where I put my point. So this represents the point right there. And we're going to spend some quality time on these later in this quarter. You all have a great weekend, and I will adjust the homework due dates and the quizzes in My Open Math, and you know which quizzes you have to do because I'll actually put the section numbers onto the quizzes, and I'll move anything that's not for 1.1 and 1.3 into next week. Have a great weekend, you all. Get caught up on your homework, and don't wait till Sunday night, please.